Today we are going to discuss the concept of field extensions. There are three main ideas. The first one is the basic goal. The second, degree of algebraic numbers over a field, and then the concept of symbol extensions. So what was our basic goal? The basic goal is to find an extension of a field f containing 0 of a given polynomial function f of x. That is, suppose we have a field f and a non-constant polynomial function f of x. Can we find an extension of f? Can we find a field containing f and a 0 of this polynomial function f of x? And the answer to that question is the Kronecker's theorem. Kronecker's theorem says that there does exist such an extension for any field f and any non-constant polynomial f of x in fx. Coming to the proof of this theorem, first of all, what we do is we find an irreducible factor of this non-constant polynomial function f of x. We know that every polynomial in fx has irreducible unique factorization into irreducible factors. Therefore, f of x does have such an factorization, and let p of x be a factor of f of x. Then we know that since p of x is an irreducible polynomial, the ideal generated by p of x will be a maximal ideal. And again, f of x is a polynomial ring, and f of x divided by the ideal generated by p of x is a field. Since the ideal generated by p of x is a maximal ideal, the ring divided by maximal ideal, the quotient ring, will be a field. Therefore, f of x divided by the ideal generated by p of x is a field. This is the field we are looking for. This is the field containing f and a 0 of this function f of x. Now we have to prove this claim. This contains, that is, the field E contains the field f, and also it contains an alpha, which is a 0 of this non-constant polynomial function f of x. We start with the function psi from f to this field E. And psi is defined by psi of A. A is an element of the field f. Psi of A is A plus the ideal generated by p of x. What it means? A plus ideal generated by p of x is the set of all polynomials generated by p of x to which a constant term a is added. A is a constant term. A is something like a plus 0x plus 0x square plus etc. plus 0. Okay, you can add any term. Okay, so practically it is a constant function a. And the ideal generated by p of x is the set of all polynomials which are multiples of p of x. 0 polynomial is there, then all other polynomials are multiples of p of x, p of x, p of x square, and other multiples of p of x, p of x into some value in f of x, f. Okay, all these values. So if b is an element of f, then b into p of x will be an element of this ideal generated by p of x. So a plus p of x is a subfamily of polynomials with constant term a. And if we define such a function psi, then psi is a homomorphism, and kernel of this homomorphism is the ideal generated by p of x. And we can clearly see that f is isomorphic to psi of f, and this is a subfield of E. And then we need to prove that there is an alpha, which is a 0 of f of x in this space E, this field E. We take alpha as x plus the ideal generated by p of x. So we find all the polynomials which are multiples of p of x. Then we add x to these polynomials, all these polynomials. Then we get the set of all polynomials of the form x plus ideal generated by p of x. And if we find the value of p alpha, we can clearly see that it is nothing but 0 plus ideal generated by p of x, or simply the ideal generated by p of x itself. This is the additive identity of the field we have generated. The ideal generated by p of x will be the additive identity of the quotient field f of x by ideal generated by p of x. Therefore, clearly alpha is a zero of p of x. If alpha is a zero of p of x, then clearly alpha will be a zero of f of x, and therefore this alpha belongs to E, and the field E contains both f and alpha. So we have achieved our basic goal through this theorem. Now we are coming to some new definitions. That is, when do we say that a number alpha is algebraic over a field f? A number alpha in an extension E of field f is algebraic over f if there exists a polynomial function f of x such that f of alpha is 0. If there exists a polynomial function f of x in fx such that f of alpha is 0, then alpha is algebraic over f. We just don't say that if alpha is algebraic. We cannot say something like that. Alpha is algebraic over a field f. Field should be mentioned for when we are suggesting that an element is algebraic, then we should mention the field. And if we doesn't mention a field, we automatically mean that it is the field of all rational numbers. What is the meaning of algebraic number? A number is algebraic, or a number is an algebraic number if it is a complex number which is zero of some polynomial function with rational coefficients, f of x in qx. Okay, so there is some change, f of x in qx. That is, the coefficients of f of x are from the rational vectors, rational field. And then we come to the concept of transcendental numbers. Transcendental numbers are numbers which are not algebraic. If a number is transcendental over f, then it is not algebraic over f. Then we have a definition called irreducible alpha over f. This is the irreducible polynomial of alpha over f. So what do we mean by this term? Irreducible polynomial of alpha over f is the unique monic irreducible polynomial p of x in fx such that p of alpha is 0. And degree of alpha over f. Degree of an algebraic number alpha over f is the degree of this unique monic irreducible polynomial. So here we started with unique monic irreducible polynomial. So so far we haven't proved that this polynomial is unique. We are going to prove that this polynomial is in fact unique. So how does we prove that? We already know that it exists. Okay, by Kronecker's theorem, there exists irreducible polynomial for any algebraic number alpha over f. If alpha is algebraic over f, then there will be a irreducible polynomial p of x such that p of alpha is 0. And we consider the evaluation homomorphism psi alpha from fx to E. And clearly we can see that the kernel of psi alpha is the set of all non-constant, set of all polynomial functions in fx such that the evaluation, that is, if f of x belongs to fx, f of alpha is 0, then f belongs to the kernel of psi alpha. So the kernel will be, so we know that every kernel is an ideal. F of x is a ring and is a evaluation homomorphism. Psi alpha is an evaluation homomorphism. Therefore, the kernel of phi alpha will be an ideal of fx. And there is a theorem stating that every ideal of f of x will be principal ideal. That is, every ideal of fx should be generated by some polynomial in fx. So there will be some polynomial p of x such that p of x generates this ideal, which is the kernel of phi alpha. The kernel of phi alpha is a principal ideal. Therefore, there exists some p of x which generates kernel of phi of x. If p of x generates this kernel, then every polynomial in this kernel will be divisible by p of x. P of x will divide every polynomial in kernel phi alpha. So if f of x belongs to kernel phi alpha, That is, if f of alpha is 0, then f of x will belong to kernel phi alpha. And if f of x belongs to this kernel, then p of x should divide f of x. Okay, so it gives some notions of uniqueness. That is, if there is a polynomial which gives 0 under evaluation, then it will be divisible by p of x, or p of x will be a factor of this function. So every polynomial function giving a 0 under this evaluation homomorphism, that is, every polynomial with the alpha as 0 will be there in this ideal. And it remains to prove that this polynomial function p of x is irreducible. Suppose this polynomial function f of p of x is not irreducible, then we have a factorization of p of x. P of x is equal to r of x into s of x. If p of x is equal to r of x into s of x, then p of alpha is r of alpha into s of alpha. But this is nothing but 0. Therefore, r of alpha into s of alpha is 0. We know that evaluation homomorphism maps functions, polynomial functions, into numbers in this extension E. So R of alpha and S of alpha, R of alpha and S of alpha are elements of this field E, and their product is 0. Since E is a field, E cannot afford to have 0 divisors. So one of them should be 0. If none of them are 0, then E has 0 divisors, and this is not possible since E is a field. Therefore, R of alpha, either R of alpha is 0 or S of alpha is 0. But we already said that R of alpha and S of alpha are factors of P of x, and of course they have some degree less than that of P of x. These are non-constant polynomial functions with the degree less than that of P of alpha, and P of x and P of x should divide them as well. Or we already said that if some polynomial belongs to this, if there is a polynomial, suppose we take that if R of alpha is 0, then we say that R of x belongs to kernel of phi alpha, and then P of x should divide R of x. This is not possible since degree of R of x is less than P of x, and R of x is not a 0 polynomial. So this is a contradiction. Therefore, P of x cannot have factors. That is, P of x is irreducible. And now we come to the concept of simple extension. Suppose we have a field and an algebraic, we are not necessarily taking algebraic number, an alpha, okay, an element alpha from an extension E of f. We are taking a field f and an extension of field f called E, and choosing an element alpha from this field E. Then f alpha is the capital F alpha is the smallest subfield of E containing both f and alpha. And this can be obtained by the image of the evaluation homomorphism phi alpha. Phi alpha of the set of all images of phi alpha. We are taking the evaluation of all polynomial functions in fx, nothing about non-constant. We are taking the image of the evaluation of every polynomial function in fx. Then we get a subfield of E, and this subfield is called the smallest subfield containing f and alpha, and we denote it as capital F alpha. And we know that if alpha is irreducible over f, if alpha is algebraic over f, then there is a polynomial, irreducible polynomial of alpha over f, which is of the form a0 plus a1x plus a2x square plus etc. an minus 1 x raised to n minus 1 plus x raised to n, where a0, a1, etc. are elements of the field f. And we also can prove that if beta belongs to this field f alpha, the field extension f alpha, then beta is of the form b0 plus b1 alpha plus b2 alpha square plus etc. bn minus 1 alpha raised to n minus 1. Every element in this extension field will be of this form, where b0, b1, etc., bn minus 1 are elements of the field f. This is a very beautiful theorem. And using this theorem, we can write all the elements of this extension field, and also we can write the tables, the addition tables. How do we add elements of f alpha and how do we multiply elements of f alpha? We can, that is, we can find the field and define all the operations, and this is the field containing f and alpha. So this is a quite useful result, and I conclude this session, this topic. Thank you.